Hello everyone, we are a group of NUA students and this video is to illustrate what is link analysis and PageRank. PageRank is an algorithm used by Google Search to rank the websites in their search engine, and it actually measures the importance of website pages. Before moving to the details, let's look at what is graph. The graph is not the conventional graph we mean, for example, the histogram and the pie charts. The graph actually consists of nodes and edges. The nodes is objects and the edges is relationships. And the graph analytics aims to understand and visualize the object relationship and to uncover if any insights. So looking at the picture, right, the objects, the nodes is the science topic, is the research paper in within different science topic, for example, chemistry and math. And the edges actually represent the citational within and between the different science topics. So one of the application is the social network. Here the nodes is person and the edges is relationships or friendships. And social network graph aims to find out the social interactions or key influence who can get their opinions or pictures liked or shared very quickly. Another example is the web search. So here the nodes is the web pages and the edges is the hyperlinks which link from one pages to another pages. And this actually determine which web pages should be ranked higher. So what is link analysis? It's an approach to compute the importance of the nodes. And it helps us to understand some of the questions using the web search as the example. It helps us to understand what are the more trustworthy web pages and what is the best answer to query platform design. Now moving to the PageRank, which is a way to compute the importance of the web pages. The basic idea is the node is the web pages and the hyperlink is the edges and the link carries a word. A page that is more important if it has more incoming links, and the incoming links is a measure of the importance and authority of the pages. We can see Stanford has 23,000 of in links, while other web pages may have 0 or 1 in link. And not all the incoming links are equal. Links from more important pages count more because the words on the out links actually is related to the importance score on the source web pages. Here is an illustration of how to compute the importance score. The nodes represent the web pages and it has an importance score. For example, the blue node has 25.2 importance score, and we can see there are 3 relatively more important nodes, which is the blue node, the orange node, and the red node. And for each node, it has in links and out links. And the out links carries the word, which is proportional to its importance score. And we can have 2 insights from this graph. A word from a more important node weighs more. We can see for the orange node, it has only 1 out link and it carries the word of 18. And we can see the red node, it also only has 1 out link and it carries a weight of 9.6. Another insight is a page is more important tend to point to each other. We can see the blue node and the orange node is actually pointing to each other. So actually how to calculate? If a page J has the importance R, has n outlinks, and each outlink has an equal share of the importance score. Therefore, each outlink has R divided by n volt. We can see for the blue node, it has an importance score of 25.2. It has 3 outlinks. So we can see each outlink carries the equal share of the total importance score. Therefore, 25.2 divided by 3 is 8.4. Similarly, we can see for the purple node, it has 2 outlinks and each outlink carries a word of 3.6 divided by 2, 1.8. For page J's own importance score is the sum of all the in-links work. We can see for the blue node, it has 4 incoming links, which is 18, 4.2, 1.8, and 1.2. All these add together equals to 25.2. And looking at the purple node, it has 3 in links, which each link has 1.2. Therefore, the total score is 1.2 times 3, which is 3.6. The flow equation actually illustrate a systematic way to calculate the score and to tell us actually the score converges. So looking at the picture, we have three nodes, node Y, node A, and node M. The RY is actually the important score on the node Y, similarly for RA and RM. So if we look vertically, each column, the sum is 1 because it actually represents the outlinks. So we can see the node Y has two outlinks. So each outlink will share the equal share of the important score RY. Therefore, node Y has one outlink point to node Y itself, which has a vote equals to 1 over 2 RY. Similarly, another outlink points to node A and have the same 1 over 2 RY vote. Similarly, for node A, it has two outlinks to node Y and M. Therefore, each node Y and M has a in-link from node A, which have the 1 over 2 RA votes. And for node M, it only has one outlink point to node A, and therefore all the RM flows to node A. And looking horizontally, it actually represents the in-links. Therefore, for the importance of RY, we can see it consists of two in-links. Therefore, it equals to 1 over 2 RA, the in-link from node A, and 1 over 2 RY, the in-link from itself, the node Y. Similarly, for node A, we have 1 over 2 RY plus RM. And for RM, we only have one in-link from node A, and therefore it has 1 over 2 RA. Now we assume initially all the nodes have the equal importance score, which is 1 over 3, and the sum equals to 1. At 0 iteration is 1 over 3, 1 over 3, 1 over 3 for RY, RA, and RM. For the first illustration, we just use the formula. So for RY, right, it actually equals to 1 over 2 RA plus 1 over 2 RY. But because both RA and RY equals to 1 over 3, therefore it's RY still equals to 1 over 3. Looking at RA equals to 1 over 2 RY plus RM. Therefore, it's 1 over 2 times 1 over 3 plus 1 over 3. Therefore, it's 3 over 6. For RM is 1 over 2 RA, therefore it's 1 over 3 divided by 2 is 1 over 6. For the second iteration, right, the RY equals to 1 over 2 RA plus 1 over 2 RY, therefore it equals to 6 divided by 3 over 6 divided by 2, which is 3 over 12, plus 1 over 3 divided by 2, which is 1 over 6, which is 2 over 12. Therefore, 3 over 12 plus 2 over 12 is 5 over 12. And after many rounds of iterations, it will converge to 6 over 15, 6 over 15, and 3 over 15 for RY, RA, and RM respectively, which is 2 over 5, 2 over 5, and 1 over 5. There is another way to compute it. You can use the formula. So from the formula, we can see RY. From the first formula, we can see 1 over 2 RY equals to 1 over 2 RA. Therefore, RY equals to RA. And from the third formula, we can see RA equals to 2 RM. Therefore, RY plus RA plus RM equals to 5 RM. And the total score initially is 1. Therefore, RM equals to 1 over 5 and RA equals to 2 over 5 and RY equals to 2 over 5. This is the same as the converged score. However, the important score does not always converge. There are two problems on the real web. The first one is called dead end. We can see the blue node is called dead end because it has no outlinks. Therefore, this dead end will suck all the important score to this node. Similarly, the second problem is spider trap. It's kind of a group of nodes pointing to each other but no links out. It's similar to the dead end, but it's a group of the nodes pointing to each other. Here is a flow equation representation of the dead end. We can see the node M is the dead end. It has no outlink. Therefore, the vertically is all 0, 0, 0, no outlink. And all the importance will be sucked at the node M. The solution is we allow the users to jump to some random pages if it's at the node M. Therefore, we assume like if a user at node M, it has like 1/3 chances jump to node Y, and 1/3 chances jump to node A, and 1/3 chances remain at the node M. The problem spider trap is the node M represent a group of nodes pointing to each other. Therefore, the node M has only one outlink and which pointing to itself. And similarly, it will suck all the important score to these groups of nodes, which is called spider traps. We also have a solution called telepause, and we assume at the spider trap, the node M, there's a probability beta. This node M will follow the outlink pointing to itself, any of the nodes within the spider trap M. However, there's a random chances probability of 1 minus beta. This will jump to some random pages, which is Y, node A, or itself. So here is an illustration. We assume the chances beta is 0.8. So there's a 0.8 chances that the server, the user, will follow the links. And there's a 0.2 chances at the node M, they will randomly jump. And we assume all the chances is 1/3. So means at any of the node Y, node A, and node M, it has random chances jump to itself to other two nodes. Therefore, that's where the 1/3 coming from. And after calculation, we can see that Ry equals to 7/15 Ry plus 7/15 Ra and plus 1/15 Rm. Similarly for Ra and Rm. There are also limitations of the page rank. For example, here is measures the generic importance of the page. We didn't include the topic specific. For example, what are the pages related to platform design? The solution is to have a topic specific page rank algorithm. And we also have other measures of importance which we didn't include in the page rank. The solution is hubs and authorities. Another thing is the link spam. So means the people who understand how the page rank works, it will purposely post something on the internet to boost the important score of its pages. For example, I will just go to some websites and comment, please go to my website, and this actually create the hyperlinks, one of the inlinks to my website, and add more importance to my website. The solution is trust rank. Our presentation won't include all the solutions and leave you to find out more on this topic.